Alright, let's spend a little time on gas laws. I'm going to emphasize the ideal gas law and talk a little bit about stoichiometry, but I want to talk also a little bit about kinetic theory so that you understand how we picture gases and why they behave the way they do. But first, let's discuss pressure. If you were to take a column that was 1 meter by 1 meter square and include in that column all the gas molecules that exist between the surface of the Earth and as high as you need to go in outer space, you would find that approximately 10 to the fourth kilograms of gas that exist in that 1 square meter column. So the definition of pressure is that pressure is force per unit area. And in physics, it turns out that you can determine the force as the mass times the acceleration of gravity, where m is the mass and g is the acceleration of gravity. Generally, the mass has to be in kilograms, and the acceleration of gravity will be in meters per second per second. If we divide that by the area, we would calculate the pressure that you feel standing on the surface of the Earth as a result of all those molecules of gas above you. And that turns out to be 10 to the fourth kilograms, 9.8 meters per second, divided by the 1 square meter area that we chose for our column. And that turns out to be 1 times 10 to the fifth kilograms per meter per square second. And in just the same way that we defined a joule as an energy unit, when in fact the MKS unit was kilogram meter squared per second squared, this unit is given the name Pascal. So the pressure at the surface of the Earth is 1 times 10 to the fifth. So the pressure on the surface of the Earth is approximately 1 times 10 to the fifth pascals. It turns out then we can also say that that's 100 kilopascals. Remember, kilo means 1,000. And it's also called 1 bar. So 1 bar is the approximate pressure you would feel standing at sea level, standing at the beach, as a result of the column of air that's above you. Another term we use all the time, and that we use quite frequently in this section, is an atmosphere. And an atmosphere is 1.01 times 10 to the fifth pascals, 101 kPas, or 1.01 bar. An atmosphere is a little bit more than a bar, very slightly more than a bar. All right, so let's take a quick look at kinetic theory just to see where all of this comes from. The tenets of kinetic theory are listed here. Gases are composed of a large number of very tiny molecules that have a large distance between neighbors. The particles are in continuous random motion. Now this is important. As long as you're not at 0 degrees Kelvin, everything is moving all the time. Gases move continuously, as you'll see in a minute, on average between 2 and 500. If you've got hydrogen, it could be as much as 1,000 meters in a second. 1,000 meters is about 10 football fields. So gas molecules are moving pretty quickly. The particles are independent of one another. They don't interact. When they collide like pool balls. The collision, we assume, is perfectly elastic. The molecules don't recoil. They just bounce off each other the way pool balls might. And Newtonian mechanics can be used to describe how a system like this should behave. And of course, that's what we observe with what we call ideal gases. So here you see 2 graphs, and it's important to make sure that we understand what we're talking about here. On the x-axis, we have speed on the order of meters per second. Remember, a meter is about a yard, and so these are, yards per second, if you will. On the y-axis, we have the number of molecules that are moving at that speed. So you can see that at this maximum here, more molecules are moving at this speed than in any other. And that speed for this particular sample is about 150 meters per second. Notice also that the distribution is reasonably narrow. By contrast, the molecules represented by the blue curve are much more widely distributed. The distribution is much broader. We would say that it has a larger standard deviation. And also, the most probable speed, in other words, the speed more molecules have than any other, is sitting just around 350 meters per second or so. In the case of the gas represented by the blue curve, both the average speed and the distribution have increased dramatically compared to the red curve. Now, the difference between these two curves might be the temperature at which the samples were observed. And you might ask the question then, compared to the temperature of the gas in the red curve, is the temperature of the gas in the blue curve higher or lower? Well, it's important then to understand that temperature is a measure of average kinetic energy. So in fact, the higher the temperature, the higher the average kinetic energy, and as you know, kinetic energy is directly related to speed. So the higher the temperature, the higher the average speed. That will mean that the blue curve represents the higher temperature and the red curve the lower temperature. Again, it's important to realize that not only does the average speed increase when you increase the temperature of a gas, but so does the distribution broaden. And that is a significant issue, particularly these days as we warm the climate. Now, if we consider these two as gases at the same temperature but with different molar masses or molecular weights, we would expect heavier molecules to be moving slower if they have the same kinetic energy. And average kinetic energy is the same for molecules that are moving at the same temperature. So temperature is a measure of average kinetic energy. Therefore, if these two graphs represent gases at the same temperature, the fact that the red curve represents gases moving at a slower probable speed, most probable speed, indicates that those molecules must be heavier, because heavier objects move more slowly to achieve the same kinetic energy as lighter objects that are moving faster. So the red curve represents a gas at lower temperature or a gas at higher molecular weight compared to the gas represented by the blue curve. Let's then look at the experimental evidence that suggests that our model, the kinetic theory model, is correct. First, we start with Boyle's experiments. What Boyle did was to trap a gas inside a cylinder, change the volume of the cylinder, and observe the pressure of the gas as he changed the volume of the cylinder. You see volume represented on the y-axis and pressure represented on the x-axis. And these are called Boyle's law curves, or Boyle's law isotherms, same temperature, isotherm, because they represent gases at the same temperature. So what Boyle was able to show is at constant temperature, the pressure times the volume equals a constant, because that's how you get a parabola. PV equals a constant, XY equals a constant. So as the pressure increases, the volume goes down. And notice the curves aren't straight. Notice also that we get a family of curves that are different only by the temperature at which the measurements were made. So that's Boyle's law. Well, Charles then replicated that kind of experiment, except this time he looked at the volume when you change the temperature but keep the pressure constant. So we have three different lines represented here, three different curves at three different constant pressures. And we see they're not exactly parallel. They're all decreasing as the temperature goes down, but we've plotted our temperature in degrees centigrade. If we were to extend this curve, we would find out that all three of the gases lines converge at the same temperature. And that temperature represents a volume of 0 liters. So the gas would have no volume. Now you may argue, of course the gas molecules have volume, and that's true. When you get down to very, very low temperatures and very, very low pressures, you have to take the gas volume into account. But What we're doing here is extrapolating from 0 degrees centigrade, where the gas molecules' volumes can be ignored because they're so small compared to the total volume of the system. And as we extrapolate down, we see this magic temperature at which all gases converge, and that is minus 273 degrees centigrade, or 0 degrees Kelvin. When we put all this together, we get something called the ideal gas law. Remember, I said PV equals a constant. We can say for the Charles law, at constant pressure, V is equal to a constant times T. So if we put that together, we have the ideal gas law. The constant we're seeking at a given temperature is R. Now, we're also assuming, because the systems were closed, that the number of moles of gas we used, which is N, the number of moles of gas we used was the same in all cases. So it too, in these experiments, is a constant because we always made it the same. Okay, so let's define terms. The pressure is usually given in atmospheres, the volume in liters, N is the number of moles, and R is a constant called the gas constant. Its value is 0.0821 liter atmospheres per mole degree. In other words, if the volume is in liters and the pressure is in atmospheres and the temperature is in Kelvin, which it must be, then R will be 0.0821. R can take on different numeric values if you change the unit. But the simplest thing to do is to stick to the 0.0821 liter atmospheres per mole degree and make sure your pressure's in atmospheres, your volume's in liters, and the temperature is in Kelvin. So this is the ideal gas law, a combination of Boyle and Charles's law.